Hey everybody, I'm back with the last installment of Fitting Models to Data. This is part 4. And so now we're actually ready to put everything together and fit dynamic models to data. So how do we go about doing that? Well, first, let's just recap similarities and differences between statistical models and dynamic models. One of the big differences is that with statistical models, we're just finding associations, right? Which is important. We can identify which variables are related to which other variables by partitioning variability and things like that, like we saw with simple linear regression. In dynamic models, we're actually hypothesizing a mechanism for how things are working that are linking things at different levels, at different scales. Another big difference is with statistical models, we assume that the responses are independent from each other. That's one of the conditions for linear regression, independence of responses. Dynamic models, there are dependencies built in, right? The probability that I get sick is not independent of your health status, right? It very much depends on how many infected people there are. So there is a dependence linked in. And what we do with dynamic models is we can take some of those things from statistics and link them. We can account for bias, we can account for random error, but we can also account for the dependence and linking things at multiple scales. And so when we get to the point where we want to fit dynamic models to data, one of the key things that we need to do is link it to probability, right? We want to be able to ask or answer this question: what is the probability that a model, for example, an SIR model, would have generated or could have generated the data that we actually observe? And so from that, what we're really asking is, what is the likelihood of a model given the data? And so when I say model here, I'm talking about like a dynamic model, and the parameters that I'm talking about are the parameters that govern how things are working in that model. So things like beta, like the transmission parameter, or gamma, recovery parameter. What's the likelihood of those parameters? And so in order to do this, we have to, it has to come from understanding likelihood. And that starts with understanding what distribution, out of what distribution did our data arise? So we saw before, when we have prevalences, a binomial distribution is a good model for that. You have a fixed number of trials, and you want to know what's the probability of a specific number of successes. So when you're dealing with prevalences, binomial distributions are often a way to go in terms of specifying likelihoods, but it's not the only one. And so you should be aware of some others. So I'm sure many people are familiar with the normal distribution. This is used for continuous variables often, or sums of other variables can sometimes be, normal distributions can be used for those as well. If you have time to an event, if those are the data that you have, you might choose an exponential distribution and use the density function for that in order to use the likelihood. Poisson distribution, similar to the binomial distribution, except now there isn't a fixed number of trials. There's no fixed n. We're just counting up the number of successes in a time frame, or in area, or in space. So the number of events in an interval. So we don't have a fixed overall number of trials. And what these are really doing is capturing the randomness in the model. So the stochastic component, the things that are the observation error, the randomness. So in order to fit models to data, we actually need data as well. So here's some data. This is HIV prevalence in Harare. And so we might think about creating an SIR model to fit to these data. How do we go about doing that? Well, these are prevalences, and so we immediately think of the binomial distribution. And so for each one of these time points, there's a different potentially binomial distribution, right? What determines the binomial distribution are the number of observations and the number of fixed trials, and then the underlying prevalence at that time point. And so for different time points, we might have different binomial distributions. Before in the example, we just talked about one instance, right? One piece of binomial data. And so in order to fit models to data, we have to understand what are the parameters of each one of these, distributions. And so in order to figure that out, we can rely on our process model. And so the model that's generating prevalence, for example. So an SIR model, for example, the deterministic component of the model. And so that also has parameters. So it's easy to get those two things confused. The parameters of distributions, probability distributions, versus the parameters in our SIR model. So up here, the parameters that we think about are, beta or gamma, right? We think of transmission parameters or recovery parameters, for example. And so that could generate, prevalence over time, cases over time. And then we use that prevalence in a binomial context to provide input for our distributional parameters. And all that taken together, we can come up with a likelihood to identify, for a given set of model parameters, what's the probability that we would observe the data that were actually observed. So let me give you an example that might help put this all together to link it. So imagine that these are our data, prevalence of a disease over time. And so we've measured these and we have error bars, but our prevalences, we have 10 prevalences over a span of 25 years. So we might come up with some type of compartmental model, an SIR model, for example, to see if we could fit these data. And so maybe we do that. We build an SIR model, and that's the prevalence curve that it generates. And so maybe we could do this informally and kind of get an idea. We're changing parameters like gamma and beta in such a way, maybe some other parameters as well, so we can see if this prevalence curve can fit as close as possible to the actual data, what actually happened. So that's informally fitting the model. But now if we want to formally fit it, if we want to come up with maximum likelihood estimates, we want to find beta and gamma, right, from our SIR model. So the probability of observing these actual data points is maximized. So how do we go about doing that? Well, so if you think about this curve here, you can see, if we look at this time point, 1983, the model says the prevalence is right around 0.1, but the observed point looks like it's about 0.09. Up here, it looks like the model is suggesting the prevalence should be around 0.18, but the observed is off by a little bit, 0.19. Here, at this time point in 1989, it looks like the model is about 0.23, but what's actually observed is about 0.28 or 29. And so we have an observed component and a predicted component from the model. And so for each one of these, we can do something similar to what we did in that binomial example from before. Here, the model is saying, well, let me pick one where they're different. So here, the model is saying 0.23. So I could use a binomial probability function and say, okay, if my underlying binomial parameter that's coming from the model is 0.23, what's the probability I would get a prevalence this big? Right? And I could find that probability for each one of these 10 points. If I assume that they're independent, I can multiply them all together, and that represents the probability of getting these data for a particular set of model parameters, alpha, beta. So the alpha, beta, or sorry, I was calling it gamma. The gamma and beta parameters from an SIR model help generate this prevalence curve, which we in turn use to help find our distributional parameters that can help give us the likelihood of identifying these data. We want to find gamma and beta in such a way that the probability is maximized. And once we do that, then we have the maximum likelihood estimates for our model parameters. And so that's what we mean when we fit dynamic, when we want to try and fit dynamic models to data. And so until recently, that wasn't always expected. A lot of the times, you could just postulate models and do mathematical things like find equilibria and things like that. But what's been happening more recently is a big push to actually tie this theoretical model world to the real world, by fitting it to data. And so more and more it's expected. And it's important to be able to fit models so we can get a better parameter estimates, we can make statistical inferences, and to compare models. And so to summarize, what we've been talking about in these videos, why do we fit? We want to estimate parameters, we want to make statistical inferences and compare models. And usually the way that we fit is tied to some probabilistic framework, for example, likelihood. And things we've talked about already about what you need to think about when you're fitting models to data. What are the conditions? What are the underlying assumptions of your model? Beware of overfitting. You don't want to fit the noise. And we can guard against that by doing things like cross-validation. How bad? Goodness of fit sometimes is optimistic, but how bad does the model actually fit? Is it good enough? And then identifiability. Can we really isolate these parameter values as being valid, or maybe one set of parameters fits just as well as another set, and we can identify the values that are really specific to a particular fit. And I think that's it. So I'm happy to discuss any of these things with people in a more informal setting, and hopefully you have a good sense of now how we fit models to data.